Okay, we are starting chapter 4. Today's pretty vocab intensive. Okay. Mostly review. Kind of what it's been up to this point. But it's pretty rigorous review, if I do say so myself. I mean, we just finished the stoichiometry chapter, which we only got halfway through the stoichiometry chapter by the end of the first semester of last year. So we start second semester finishing the stoichiometry, and we're already through it the first month.
You mean the advanced chem or just chemistry? Oh, okay.
Not advanced.
It shouldn't have taken that long for you.
And regular chemistry. So it's quite a bit faster paced. Okay, now we will get to new stuff. Don't worry. Okay, don't worry. You're not worried? Okay, good. All right. So this chapter is really about solutions. Okay, solution chemistry can be tricky if we don't understand stoichiometry type ideas. What I mean by that is knowing things like when I have a substance that looks like that, and I know that it completely dissociates, okay, what it would mean as far as what it would break down into. Okay? If I have two of these particles and it completely dissociates into my two polyatomic ions, I have 6 of those. And I have 2 of those. Okay, and that's important because when we start doing things in solution, they usually give us concentration based on the thing put together. So if this were like a 3 molar solution, what would be the molarity of that? 9 molar solution. Because of the 1 to 3 ratio. Okay? And we'll get more into that later. I'm not going to spend too much time talking about that now. But being able to see proportions, for example, if I got an acid that looks like this, and I know this is a 3 molar concentrated acid, when you get into doing acids and bases, what's really important? That, right? It's been a while. I know it's been a while since we've done acids. Okay, but the hydrogen concentration is what's important. That's what tells us pH. So if I know about a 3 molar HCl solution, what's the molarity of my hydrogen? 3. Believe it or not, this is difficult for a lot of kids to make this connection that if I have 3 moles of this, well, how in the world does, if I have 3 moles for every 1 liter here, and I have 3 moles for every 1 liter here, does this mean I have 0 moles for every, how does this work? No. How many moles of this do I have? 3. So how does 3 plus 3 equal 6? Because remember, moles is a particle number, right? How many pieces? Well, these pieces are smaller than this piece. Okay, so is it possible that more pieces make up a smaller amount of pieces but a bigger substance? Okay, that's an important thing to be able to figure out when it comes to solution chemistry, because solution chemistry is all done, or mostly, or typically done, from at least what we're going to talk about, in water. Okay, water is very, very unique in its ability to dissolve. One of its major properties is that it can pretty much dissolve, I don't know, not everything obviously, but it dissolves a lot of things.
This is an acid and a base.
What?
This is an acid and a base.
Yep. Well, that's not the only reason, but one of them. Okay, it has a lot to do with its properties. Okay, so we're going to spend a lot of time talking about solution chemistry. A lot more of it will be second semester, but a lot of chemistry happens in solution. AKA happens in water. And the reason why, what is most of our Earth made out of?
Water.
Water.
Now, it makes.
Okay? And since it dissolves things and mixes well with stuff, that's another reason. Okay? Now, let's talk about the water molecule. I know this is not earth-shattering news, but you remember the structure of water. What's its geometric shape? Anybody remember?
Oh, it's a lot of We're going to have to, I guess.
What do you call it?
Yeah, I know.
Yeah, T.
Starts with a B.
B.
Bend.
Yeah.
I don't even remember off the top of my head. I don't know the different. I don't
What's the
make you guys know it, so
Okay.
I don't know it off the top of my head.
The anagram.
Anagram?
Yeah.
Oh, tight pants.
Tight pants be lame.
Tight pants be lame. Tight pants be lame, lame, lame. Yeah. Well, don't worry. You'll get 8 others that will have to know this year.
Oh, okay.
8 others. Yeah. So I have like 16 geometric shapes you'll have to know. Don't worry. But you already got the tight pants be lame, lame, lame down. You just gotta get. You don't remember that? Oh, you were 2 years ago. Tetrahedral tight pants. Always.
Man, I think
P? Start with the P. Oh, pyramidal. Wow. Dumb. Tetrahedral pyramidal. Bend. Linear. Tight pants. Be lane.
Other than tight.
Trigonal planar. Bent. Linear. 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 Yeah. Well, it's yeah. Anyway, we'll get to it. Okay. So let's just talk about some things that are really, really important here, aka polarity. What's polarity?
how they attract stuff.
Okay, that causes polarity.
It's unequal sharing of charge.
So polarity just simply means opposite regions of opposite charge.
Yeah.
That's all polarity means. Now, there's a big reason or a big why behind why things have polarity, right? Your guys are talking more about the why versus what chemically polarity is. Okay, and polarity is usually the result of what really important concept that we probably should review. Electronegativity, right? Okay? And I think, Grant, you were kind of saying more about electronegativity when you were saying attractive things, right? So, do you guys remember the trends for electronegativity?
Going
It's
down
gonna walk
into
to
the
the right.
radius. So the radius is small. Francium's the most electronegative.
Opposite. It's the biggest. So francium's the biggest radius. Remember, they're opposites. Because if you think about it, if you've got a big radius, electrons are really far away from the nucleus, and so therefore it's probably not attracted to the nucleus very strongly, correct? Okay? So then we gotta go up here. Fluorine is the smallest radius. Electrons are really close to the positively charged nucleus, and so it holds onto them very tightly.
container could store if it's that.
Some sort of airtight vacuum thing. Yeah, I don't know.
It has to be really unlikely.
Well, yeah, that's why you have to do it probably in a vacuum where there's nothing.
Yeah.
It's just very reactive. Okay? And so electronegativity essentially is because you have such a more exposed nucleus, it has a very strong pull on any electrons near it. Okay? And oxygen is probably your second most electronegative. So remember, this is going to be a covalently bonded guy. Do you guys remember how to know if it's covalent or not? Metal or non-metal is what? Nope. Ionic. And what is covalent? Two non-metals. Guys, we did the whole naming stuff. You had to know that, right? You gotta know that. That's important. Okay? Now, why? So what happens with electrons in covalent?
They're almost there.
They're sharing, right? And the big question here is why are they sharing?
Because they're closer together.
What do you mean by closer together?
Like their electronegativity.
Yes, okay, so non-metals, by the trend of electronegativity, right, tend to have stronger electronegativities, which means they have a strong pull on electrons, or they desire the electrons pretty significantly. So if you get two guys that want electrons that can bond and form a stable compound, the only way they're going to do it is if they what? Share, because if one tries to take, first of all, one can't because the other one's got such a strong pull, and so they kind of meet halfway in between, if you will. Okay? So, we have talked about how there's such a thing as polar molecules and nonpolar molecules. You guys remember that?
Yeah. So dipole.
Yeah. Dipole moment will tell us whether it's a polar or nonpolar. What's the difference between a polar molecule and a nonpolar molecule?
In the polar molecule, they have opposite regions of opposite charge.
And in a nonpolar molecule,
They do not have opposite regions of opposite charge.
does that mean they don't have charge?
No.
Let me show you, for example.
Overall negated.
So this guy is a nonpolar molecule. Do you remember the method we used to determine just by looking at it if it's polar or nonpolar? The symmetrical test. Okay, and here's what's going on. Off the top of my head, I want to say carbon's more electronegative, but it's very close. I think hydrogen's like 2.1. I can't remember what carbon is. When do we talk about electronegativity yet? I think we reviewed.
You could just put phosphorus there instead. And you know the answer. You could just replace carbon with phosphorus and you know the answer.
Well, yeah, but I'm not doing phosphorus.
Okay.
Where are you? Maybe I'm jumping ahead more than I am.
You didn't wish you well in class. How many six was it? You guys just didn't do well in
She told us after we took the test. She didn't tell us before.
No, I can't find it. Anyway, let's just assume that carbon is the more electronegative guy. This means these electrons in here are going to be pulled more predominantly that way. Okay, so the electrons are going to be closer to the carbon and not on the outside. So our partial charge in the middle is going to be negative. It's probably going to be 4 negative too because it's got 4 parts pulling electrons toward it. And the outsides are going to be what? Notice how the outsides have a partial charge, right? What makes it not polar then? Because I thought charge had to do with polarity.
It's not opposite charge.
Okay? It's not going to be opposite charges. And the reason why is because you're not pulling in opposite directions. You got electronegativity values that, if you had perfect electronegativity values like hydrogen bond with hydrogen, you've got no, it's completely perfectly shared. Okay? And so this isn't going to be attracted, right? It's not going to be able to have one side be attracted to negative things and the other side be attracted to positive things. Okay? This guy, however, do we remember which is more electronegative here?
Oxygen.
Oxygen. Okay, so our dipole moment, if you will, would look like that. There's your little plus sign.
You know what that is?
No. Didn't make that connection before?
Not so just an arrow.
Well, it is an arrow,
Showing the
but
direction.
the reason why they put that little slash there is to represent where the positive side is, and the arrow's pointing towards where the electrons are going.
I didn't know that.
Right? So the pull of electrons is up, and the positive side is the opposite of it. Okay? So, because of this, these guys then have a very, very good ability to dissolve things. Why?
Because it's polar.
Well, partly, but it's very polar.
Yeah.
There's a big difference in electronegativity here, so these are strong charges, stronger than the typical polar charges. And because they have opposite regions, when you take something like table salt, which we know that's a positive ion, that's a negative ion, if this was all positive stuff, where would what would the sodium be attracted to?
The chlorine.
Yeah, nothing but the chlorine.
Yeah.
Okay? But if I have a whole bunch of water molecules here in a circle, all the oxygens are facing towards the middle, could the sodium be right in between and be attracted to all the oxygens of the water molecules around it?
Yeah.
Okay, and could I have the chlorines be attracted to all the hydrogen sides of the molecules, and could those surround it and completely dissolve it?
Yeah.
Yes.
So, water's good at tearing apart ion compounds. Is that why
It's twofold. We won't get much more into the why behind dissolving, because it's really twofold. It has to do with inter and intramolecular forces, but it also has to do with entropy. Guys, things are more disordered when they're dissolved than when they're together.
that's true?
So it has to do with entropy. In fact, from an energy standpoint, dissolving salt is endothermic. It's only slightly endothermic, but because there's such a high entropy difference, it does it pretty readily. Even though energy suggests it wouldn't happen.
So why do things precipitate that?
It's because things are more attracted to the solid form than it has to do. Remember, I said inter and intramolecular forces do play a part. Okay, so essentially what happens is if you're intramolecular force. First of all, do we remember what those words are?
Yeah. Intra is within, inter in between, right? Or is-
Okay, yeah, that's true. But context here. What's the intra?
The bond between
These bonds.
yeah.
Inter would be a partial negative side of one molecule attracting a partial positive side of another molecule. Okay, which one is typically stronger? Inter. Okay? Sorry, intra. Did I say inter?
Yeah.
Intra, the within, is going to be stronger. It's way easier to separate partial charges than complete charges. Okay? One other thing that's really important is this difference. If you've got strong intermolecular forces that are strong enough to overcome and help break apart intra, now, yes, intra is always stronger, but remember it's not just that and that alone that allows something to dissolve. Remember, there's an entropy point to it, and there's some other little factors that play a role. Because if it was just between inter and intra, which would win every time? Intra. Okay, so it's never one factor in chemistry, unfortunately. There's a lot of pieces playing, and we'll get into that much more later. Yeah, we don't have a lot of time, and I really haven't gone through any of this stuff. I'm just trying to set the stage, doing a lot of review here. Most of today is just vocab related. Okay, aqueous solution. Remember, if I have something like this, we abbreviate AQ. What does that simply mean? It just means that you have this particular compound that has been dissolved in what?
Water.
Water. Can it be dissolved in anything else?
No.
No. Well, I mean, it could dissolve in something else, but we wouldn't call it aqueous.
Yeah.
Okay? Pretty straightforward. Alright, we've kind of talked about polar molecule, opposite regions of opposite charge. Doesn't necessarily mean that a molecule that's not polar doesn't have charge, just means it's not opposite charges on the opposite sides. Okay, this is just simply going to be like water surrounding sodium and chlorine particles. That process is called hydration. That'll come later when we start talking about energy of hydration and things like that. Probably next semester, but just want to get the vocab word out there. Solubility. Okay, we're going to spend a pretty significant portion, I don't know if it's this chapter or if it's later, talking about solubility. You guys have heard of saturation, right?
Yeah.
Saturation just means you've got the maximum amount of particles dissolved in solution as you possibly could. That's also known as the solubility of that particular solution. Okay? So if you had two things combined where the solubility was lower than the amount of particles could actually be in there, it would precipitate out. And if not, it will stay dissolved. And we'll talk about that process more when we get into equilibrium. Second semester is really all equilibrium. So essentially, it's the dreaded chapter of chemistry the whole semester. Well, good. That's because I made it sound like it was the awfulest thing in the world. Okay. All right, you should know these. Yes? Familiar? I'm assuming?
Yes.
Very familiar. Solute is going to be the guy that what?
It's the cooler toner.
Okay, and solvent is,
Water.
well, it doesn't have to be water, but it is the universal solvent, right? Because there's so much of it and it does it so well. Okay? The big thing here is, what is always the case for a solute? That's not, how do I word this? I don't want to do this.
Just less of it than the solvent.
Yeah. Okay. That's what I want. The solute will always have less than the solvent. I mean, you can't take something that's 60% and dissolve it to 40%. That's not possible. Yeah.
So if you have a bucket of sugar and you put drops of water, would sugar be the solvent in that? Or
Well, there just wouldn't be any dissolving, so it wouldn't be neither.
it wouldn't dissolve at all?
Maybe you have like a couple atoms.
But it has to be a lot more water than sugar.
Well, you might have a solution, but you couldn't isolate it.
That's true.
I mean, yeah, that one's a difficult one. I'm not sure what they would classify that as. All right, electrolytes. You hear this all the time in sports type settings.
Gatorade, no electrolytes.
Okay, you know Gatorade actually doesn't have that many electrolytes in it?
Yeah, you drink salt water.
Okay. Yes. In fact, I read an article about, I think I'm going to share this with you, about LeBron James and his cramping. And how, you know, his cramps were not just these little cramps, they're the cramps that literally you couldn't move. And it has to do with his inability to maintain electrolytes in his body. And they talked about this other guy who was in like the D League or something like that, who would have massive cramps by like the beginning of, end of third quarter, beginning of fourth quarter, and he just couldn't, and they found out, research found out that he was losing like 4 times the electrolytes the average person was. And so he had to like drink salt water throughout the whole game. Yeah, it sounds awful. But it's not that bad, he says. I mean, it wasn't, I'm sure it wasn't like super concentrated. But do you guys remember, I don't know if I did this in with you guys or not, but one year I actually had someone brought in a Gatorade bottle and we used that little light bulb thing that you put in the water and it turns on if it conducts electricity and it does it. You guys remember that? But Andy's not like, you have no idea.
I have no idea.
Yeah, and so when you put it in the salt water, the light bulb just poof, bright. Because there's so much electricity.
I know what you mean.
Or so many ions in solution that it conducts electricity extremely well. Well, the Gatorade doesn't have that many ions in solution. And so I can't even remember if you could even see the light bulb. Maybe it was like really, really, really like dim. Okay? So here's really the main thing for electrolytes. A good electrolyte is something that conducts electricity very well. And it's the result of a lot of ions. The more charged particles you have in solution, the more charges can be carried through and create a nice current of electricity that can go through. If you don't have that many charged particles, you're not going to be able to have electricity travel through the solution very well. Okay, so non-electrolytes are just simply things that probably don't even conduct electricity. For example, sugar can be dissolved in water, right?
Yeah.
But it doesn't break up into ions. That's one of the rare things where water molecule actually surrounds the complete sugar molecule. And so that doesn't conduct electricity at all because it doesn't break up into ions. It's a non-electrolyte solution.
What if you dissolve multiple things at once in the same water?
I mean, that's possible.
I mean, but would it, like, if you did sugar and salt, would it conduct?
Yeah, just probably not as well as all in sugar.
Interesting.
Yep. Right? Because you would have charged particles in there, just not as much.
It wouldn't be close together either.
Yeah. But they're in rapid random motion, so it's constantly moving. Okay? And weak is just in between. This usually is the result of things that only partially dissociate. We will talk about this when we get to acids and bases a lot. Because some acids completely dissociate, and some acids only do so partially. So some of them get surrounded, but stay in their combined form. And a small amount of them will break up into ions, but only a small amount. Okay? And you guys remember strong acids, strong bases, and weak acids and weak bases way back. I guess that was probably the most recent thing that you guys have learned from last year, because it's like the last chapter we did last year. Okay? So strong electrolytes are in a complete dissociates, and the reason why is because if it completely dissociates, you have a lot of what in solution? Ions. And ions are the things that are the charge carriers. Alright, almost done. Is that it? Okay. I've kind of covered most of this already, but there are your three types of strong electrolytes. Soluble salts, because salts, when they dissolve, completely dissociate or break apart into what? Ions, and lots of them.
Yeah.
Strong acids completely dissociate, strong bases completely dissociate, and just like number one, you have a lot of what? Ions. So strong electrolytes are simply ones that have a lot of ions and therefore conduct electricity. All right, just a quick review of an acid. Acid is something that produces what? Hydrogen, but the key thing here is it's producing in a what? Ions. Now, strong acids are ones where it completely gives off all of its ions. A weak acid is one that only dissociates a little bit, and most of it stays in its combined form. If it's in its combined form, right, its combined form is neutral from a charge standpoint, right? Okay? Same thing with bases. And there's your weak, they only slightly dissociate. So these would be your weak electrolytes. So most of today has been vocab driven, vocab based, but it's important because we're going to talk about all of these things as we progress along. Questions?